Students, this is a more typical solubility problem. They're giving us the KSP values and asking us to solve for the solubility. So whereas in the previous question, or at least question 1, they gave us solubility directly and asked us to find KSP. In this case, they give us KSP, which is typical. You could look up the value of KSP for any salt, and then solve for the solubility. Remember, there's a little terminology. The word solubility means the value of X in the ice table. So in this problem, they're asking us to solve for the solubility. And just like any solubility problem, we need to begin with a good dissociation equation, which involves recognizing the ions that make up each of the salts. So for my question in part A, we start with lead 2 iodide. That's our solid salt. When it breaks apart, it will produce aqueous lead 2 ions and aqueous iodide ions. Crucially, notice that you need a coefficient 2 in front of the iodide in order to make the equation balance. That will affect all subsequent calculations. Let's make the ice table. Solids drop out. You can presume 0 for the initial concentration of the ions, and according to the Chatelier's principle, we'll shift to the side with the zeros. So we're left with X and 2X for our equilibrium concentrations. Now let's write an expression for KSP for this salt involving its ions. Notice that we take product concentrations, raise them to the power of their coefficients, and if it weren't a solid reactant, we would include that in the denominator of the equilibrium expression. But in this case, the reactant is a solid, and so it does not belong in the equilibrium expression. Next, we'll plug in the values for concentrations of each of these ions that we found in the ice table, X and 2X. Notice that you might say, hey, there's a coefficient in front of the X for iodide that's a 2, and there's an exponent 2. Yes, there is, and you need both of those. It's important not to lose one of them. If we take the expression 2x quantity squared, we end up with 4x squared, and that also needs to be multiplied by x. So that works out to be 4x cubed. Now in the problem they gave us the KSP for this salt, 1.4 times 10 to the negative 8th. So this whole expression is equal to 1.4 10 to the negative 8th. If we divide by 4, and at this point you can pull out your calculator, and then once you divide by 4, take the result and take the cube root, or that's the same as raising it to the 1/3 power. We get a value of x equal to 0.0015. And that's your answer for part A. So when they're asking for solubility, what they're asking for is the value of x in the ice table. And what we worked out was the numerical value of x. So that's our answer. Now to part B, they give us a different salt, calcium carbonate. And just like in part A, we'll begin by writing a good dissociation equation. When we make the ice table, the solids drop out. And notice that since the coefficient for both of these ions remains a 1, the ice table is pretty straightforward. We'll write an expression for KSP. It's calcium concentration times carbonate concentration. And again, since the reactant is a solid, it drops out of that expression. So it's x times x, that's x squared. And in the original question, they gave us the value for KSP for this salt, which is 8.7 times 10 to the negative ninth. And if they want us to find x, or the solubility, we would just take the square root of that. So the root of 8.7 10 to the negative ninth works out to be 9.3 10 to the negative fifth. And that's our answer for the solubility of calcium carbonate. Part C. The salt they gave me for part C was silver phosphate, Ag3PO4. Just like the other parts to this problem, we'll start by writing a good dissociation equation. Notice that we need a coefficient of 3 in front of the silver ion in order to make this work. And just like before, after fleshing out the ice table, we'll write an expression for KSP and plug in the values that we know. Note that the silver concentration must be cubed because of the coefficient 3 that we needed in the ice table and in the dissociation equation. Okay, so now we plug in values from the ice table. We had found that the equilibrium concentration of silver was 3x. We'll take that whole thing in parentheses and cube it. And for phosphate, it was just x. So 3x quantity cubed, that's 27x cubed. And we still have to multiply by x. So that gives us an expression in terms of x of 27x to the fourth. In the original question, they gave us a KSP value of 1.8 10 to the negative 18th. We'll divide that KSP value by 27 and then take the fourth root of that, or raise it to the 1/4 power. And after doing that math, x works out to be 1.6 times 10 to the negative fifth. And once we've got x, we then have the solubility for that salt, and that's what they want for our answers.